Okay, so just to wake you back up to carboxylic acid, have a little go at naming those three. Okay, so the first one you should have got is butanoic acid. The second one is 2-methyl-butanoic acid, and you must note there that the carbon of the carboxylic acid group is carbon 1. That makes the methyl be on the second carbon, so your carbonyl carbon is always carbon 1. And that does mean that the last one there is 3-methyl-hexanoic acid. So what we're going to look at in this lecture is carboxylic acids and their derivatives. What we need to be able to do is describe the structure and properties of carboxylic acids. We need to know the common reactions of carboxylic acids. We need to describe the structure, synthesis and hydrolysis of fats and oils, and then also describe the synthesis of soap and biodiesel. So to start with, you should recognise this generic acid where R could be any sort of alkyl group, and the carboxylic acid consists of a carbonyl with an OH off that carbonyl carbon. It's often written as COH or CO2H. You wouldn't write it CHOO or CHO2. You must write it COOH to show that that hydrogen is on that oxygen rather than on the carbon. Now, obviously, because hydrogen can only form one bond, these must be at the end of the chain. They are terminal functional groups. They're only found at the end because you can't have anything on the other side of the hydrogen. They finish that carbon chain. In terms of naming, as I said, the C containing the carboxylic acid is carbon number 1. So your carbonyl carbon is carbon number 1. The suffix is oic acid, unless it's with benzene, in which case the suffix is carboxylic acid. So benzene carboxylic acid rather than benzeneoic acid. So that one would be benzene carboxylic acid. So 2 examples for you there. So that first one you should see is an example of a propanoic acid, and it's got a bromine on the second carbon, so that is 2-bromo-propanoic acid. This bottom one, that is benzene carboxylic acid. So as I said on the previous slide, instead of just calling it benzoic acid or something like that, it's benzene carboxylic acid. Okay, looking at some physical properties then. So they have higher melting points than with alkanes that have a similar MR. The explanation for this higher melting point is that because there is an OH, you have hydrogen bonding between the molecules, which you wouldn't see in the alkanes. These are the strongest type of intermolecular force, particularly in comparison to the van der Waals that you'd see in the alkanes, and therefore you need a relatively large amount of energy to break those intermolecular forces. So you may be asked to draw diagrams. You can see that this shows you the hydrogen bonding diagram. And if you remember from structure and bonding in year 12, you need to make sure you show both lone pairs on the carbonyl oxygen. And then you put the dipoles on, the partial charges, and your hydrogen bond must come on from the lone pair of your carbonyl oxygen to the partial positive hydrogen of the neighbouring carboxylic acid group. So you must make sure you've got all lone pairs, all dipoles, and that hydrogen bond clearly comes from not just the oxygen, but one of its lone pairs. Okay, in terms of solubility in water, they are soluble, and that is because, again, there is hydrogen bonding between acid molecules and water molecules. This diagram just demonstrates that. So you can see that the OH hydrogen can bond to the oxygen's lone pair in water, and also the carbonyl's oxygen can use one of its lone pairs to hydrogen bond to the hydrogens in the water. So you can see that that hydrogen bond will allow them to be soluble in water because they're interacting with the water molecules. So anything up to and including 4 carbon chains, so butanoic acid, will be soluble in water. Anything sort of longer than that, and the fatty part, the long alkyl chain, can get in the way of that hydrogen bonding and disrupt it. So the solubility will decrease the longer your carbon chain. So you can now describe the structure and properties of carboxylic acids. We're now going to look at the common reactions of carboxylic acids. So first one is obvious, they are acids. So you've got your carboxylic acid on the left, they can dissociate to form what's called a carboxylate ion and a hydrogen ion. And it's that hydrogen ion that causes the acidity. Now, this is an equilibrium, and it's very much to the left. All carboxylic acids are weak acids because that equilibrium is very far to the left. There is actually a relatively small amount of dissociated H+. So the pH will not be massively low. They are quite weak acids due to this only slight dissociation. As I said, that H+ there is what makes these acids. Now, the reason that they can dissociate at all is because of the stability of this carboxylate ion. So rather than that negative charge on your carboxylate ion being localized to that oxygen, it actually delocalizes across the oxygen-carbon-oxygen of the carboxylate group, and that's shown in green on this slide. So that negative charge is shared across 3 atoms rather than being localized to 1, and that stabilizes that negative charge and allows it to exist in that dissociated carboxylate ion form. So that gives you the exam points that you would need to make to explain this unusual stability of the carboxylate ion. So negative charge can be delocalized over the 2 oxygen atoms and obviously the carbon in the middle. The more stable the carboxylate ion, the stronger the acid is. So if you can stabilize that carboxylate ion even more, you will get more dissociation and it will be more acidic, lower pH. The way you can do that is to use electronegative atoms, as they will withdraw away electron density. So if your R group was, say, a carbon with a chlorine on it, that would add extra stability to the carboxylate ion because it would withdraw the negative charge away a little bit and sort of share the burden of that negative charge a bit more. So electronegative atoms will increase the stability of the carboxylate ion, thereby increasing the acidity of the carboxylic acid. So this slide just shows you an actual reaction of an acid and a base. So in this case, we're putting an acid with a carbonate, which is a base, and that will make us a salt, water, and carbon dioxide. An observation for this would be effervescence caused by that carbon dioxide gas. So that is an example of the carboxylic acid reacting as an acid with, in this case, a carbonate as the base. Okay, another reaction is esterification. So this is the making of esters. So in an ester, the OH group is replaced by an OR, so another alkyl group. R and R dash, as is shown in this, could be the same or they may be different. So R might be a methyl group and R dash might be an ethyl group. Okay, so this shows you us making our ester using a carboxylic acid and its reaction with an alcohol. So the alcohol is the HOR2 there. So that's just any old alcohol. And R1 in the carboxylic acid and R2 in the alcohol may be the same, they may be different. It doesn't matter, you can have either way. It's done in the presence of a strong acid catalyst. So your H plus there is your strong acid catalyst. So usually something like phosphoric acid or H2SO4. It's quite a slow reaction, which means we usually reflux it to try and speed it up a little bit. And they are usually quite low yielding. The reason for this is because it's an equilibrium. So you won't get 100% yield of the product. There will be some of the reactants left over. Now, just to remind you what reflux is. So in the exam, if you're asked to explain reflux, the exam points are given there in the blue box. So reflux is where we heat a mixture to its boiling point for a prolonged period of time. We put a condenser on top of the reaction flask, and this means that any vapour that is formed and escapes the mixture is condensed in the condenser and returned back into the liquid mixture. And this just allows us to heat these reactions to the boiling point. Normally, if you heat a reaction to a boiling point, obviously the solvent would evaporate, it would dry out. So refluxing is just a way of heating it to its boiling point without the reaction drying out and any volatile reactants evaporating into the atmosphere. So that is what reflux is. You also need to know some uses of esters. So there are 4 in the top right there. We can use them for perfumes, flavourings, solvents and plasticizers. You just need to learn those uses, as you may well be asked to just quote them. Okay, in terms of naming esters, it can be a little bit tricky. You have to be very careful because they can actually flip them over and have the carboxylic, what was the carboxylic acid on the right and the alcohol on the left, or you could have them the way I've got here. So you can't remember from how they're drawn. You have to know that the alcohol, the bit that came from the alcohol, comes at the start of the name. So if you look at the left-hand example I've got here, the part that came from the alcohol is in blue, and that is a methyl. So CH3 is a methyl. The part that came from the acid is in green, and that will have come from ethanoic acid. So this one is called methyl from the blue bit, ethanoate from the green part. So the singly bonded oxygen side, alkyl group, comes first. So if we look at the one on the right-hand side, again, the singly bonded oxygen side, the blue bit in this case, will come first, and that's got 2 carbons in it, so that is an ethyl. And again, the green bit is an ethanoate, so this one is ethyl ethanoate. Okay, in terms of hydrolysis of esters, so whilst we can make our esters using alcohol and carboxylic acid, they can equally be hydrolyzed back to that alcohol and carboxylic acid. And there are 2 ways to hydrolyze esters, shown in the blue and in the red. So the first way is essentially the opposite of the esterification we looked at before. That is the same reflux that we were looking at before. So in the same way as you can react an acid and an alcohol together in the presence of a strong acid to make an ester, that ester can also be hydrolyzed in the presence of a strong acid catalyst and water. That is why that red route is a poor yielding for both making the ester and hydrolyzing the ester, because it's an equilibrium. So you would have to find a way of controlling that reaction to get whichever you wanted, the ester or the acid and alcohol. The blue route, however, so if you want to hydrolyze an ester, you could also use base rather than acid. In this case, you make the salt, because as good as you'd make the acid in the presence of the base will become the sodium salt in this case. Now that salt will be in solution with the alcohol. However, what you can do is evaporate the methanol off and then add a strong acid to protonate the carboxylic acid to make the original carboxylic acid that you were after. So the bottom route is often considered better, because whilst you do initially make the salt of the acid, if you get rid of the methanol, you can then add a strong acid and reprotonate and get the carboxylic acid that you are after. You would need to get rid of the methanol before you did that. The reason being that if you acidify that reaction, you will simply set up the red equilibrium at the top of that slide, because you'd have an alcohol and an acid in the presence of a strong acid catalyst. So you do need to get rid of the methanol before you acidify the solution. That's what that's explaining there. Okay, so where we are at, we can describe the structure and properties of carboxylic acids, and we now know some of the common reactions of carboxylic acids. So let's start having a look at the structure and synthesis of fats and oils. So essentially, fats and oils are esters of long-chain fatty acids that have reacted with glycerol. Now, glycerol is the molecule on the far left there, so it's propane 1,2,3-triol. That's its IUPAC name. Your fatty acid is the red carboxylic acid you can see on the left-hand side there, where we've got 3 of them. What we mean by a fatty acid is that the alkyl chain is very, very long. So in this case, X would be 10, 20, 30. So a long alkyl chain is known as being fatty. So a fatty acid is a carboxylic acid with a very long carbon chain. Now, in the same way as we were looking at before, you could take your carboxylic acid and you could esterify it with glycerol. Now, obviously, glycerol is a triol. It's got 3 OHs, so it can do this with 3 molecules of your long chain carboxylic acid. And when you do that, you will get 3 molecules of water released, and you will make 3 ester linkages. So if you look at that big molecule on the right-hand side, the ester, the new bond that's made, is the black one between the blue oxygen and the carbonyl carbon. So you can see in blue is the glycerol molecule, what's left of it. The glycerol molecule loses its 3 black hydrogens. They go off into the water. And the carboxylic acids lose their OH. And the blue oxygens in glycerol join to the red carbonyl carbon in the carboxylic acid. And that happens 3 times to make these long chain fatty acids, esters, of these long chain fatty acids and glycerol. So that on the right hand side there is a fat or an oil. It's the ester of a long chain fatty acid that's been esterified with glycerol. Okay, so on this slide you can see the vegetable oil or animal fat, that's the ester of the long chain fatty acid and glycerol. If we hydrolyse that ester using base hydrolysis, we will make the glycerol that we started with. We'll get our alcohol back, or our triol back, and we'll also make the salt of the long chain fatty acid because we've done it in basic conditions. So you can see it's the bond that's indicated with the red squiggly lines. They're the bonds that are broken to give you back your glycerol and your salt of your long chain fatty acids, and you'll get 3 molecules of that salt. It's actually these salts that are essentially soap. So this is how we make soap. We base hydrolyse vegetable oils or animal fats, and that makes the glycerol, gives you your glycerol back, and the salt of the fatty acid, which is the soap. Another thing we can do with these is called transesterification. So you can see that in this case, we've got our, on the left-hand side there, we've got our big fat or oil, we've got our ester of our long-chain fatty acid and glycerol. Rather than hydrolyzing them, we could react them with methanol and convert the ester into the methyl ester, rather than the ester with glycerol. So you can see that you will make 3 methyl esters. Each of the purples on the left-hand side, each purple section, will be broken off by breaking the black bond, and you will make a methyl ester on that carbonyl. So this is called transesterification. You're basically taking one type of ester and making a different type of ester. The reason we do this is that these methyl esters of long-chain fatty acids are used as biodiesel. So we transesterify these big fats and oils that you've got on the left-hand side with methanol to make methyl esters, which are used for biodiesel. So the reason that we're interested in biodiesel is it can be considered carbon neutral. The reason is that the amount of CO2 given out on burning equals the amount taken in during plant growth. So they're considered carbon neutral. However, they're not fully carbon neutral because it doesn't take into account any energy that's required for the processing and transporting and so on of the biodiesel. So it's only the sort of burning of it that's considered carbon neutral, not the actual sort of processing and transporting, etc. And also this can have an effect on land available for food production, which is obviously not a good thing. Okay, so we can describe the structure and properties of carboxylic acids. We know the common reactions of carboxylic acids. We know the structure, synthesis and hydrolysis of fats and oils, so using glycerol and long-chain fatty acids. And we can also describe how the fats and oils that we can make can be broken down using base hydrolysis to make soap, or can be transesterified to make biodiesel.